galaxies, in particular the case of LINERs. I will tell you what they are. And so the first thing I'd like to tell you is that it's, as usually in research, this is a work made in collaboration. So the main collaborators are there, women, all of them, by chance. So there are Laura Hermosa Muñoz, Sara Cazzoli, Josefa Masegosa, Marta Puig-Subirá, Omaira González Martín, and Lorena Hernández García. So I want to name them because we share the workload, so I think it's a need.
Use this to change the slides.
Thank you. Is there a laser?
Yes.
Because if there is a laser, there's the possibility of me pointing towards you with the laser. So just a kind of an outline of what I'm talking about today. I've made quite a bit somewhat long introduction just to put in context everything, because it's a diverse audience. So just for you to know what I'm talking about. So I will explain a little bit of what an active galaxy is, what is the unified model of AGN, and what is the relation to the supermassive black hole, and when a galaxy is active, I'll be brief, but just to make you know, then why LINERs and how LINERs, and why outflows and how outflows in LINERs. So I'll say a few words on the future, but because it's a work in progress, but anyway, I'll try to put you in context of the work we have been doing in LINERs. So first of all, what's an active galaxy? An active galaxy is a galaxy hosting an active galactic nucleus, and that's the stupid definition, because the thing defined is within the definition itself. So in fact, what's then an active galactic nucleus? An active galactic nucleus is a compact region at the center of a galaxy that has a much higher than normal luminosity. And with this luminosity, this emitting region has properties or characteristics that indicates that it is not produced by stars. And this non-stellar emission is found in the complete spectral window. I mean, the whole spectral energy distribution from radio to microwave, infrared, optical, ultraviolet to X-ray, and gamma rays everywhere. And so, if there are no stars, what's the origin of this luminosity? This results from the accretion of matter into a supermassive black hole in the center. And just to give you a very brief history of how or when AGNs were studied in our research life as a community. The first observations made in the visible at the beginning of last century, with peculiar emission in the well-known galaxy NGC1068. But then it was Carl Siffert, who is in the 40s, made a sample of galaxies that hosted a very bright nuclei. In fact, also made a sample, and in fact, saying that later on it was said that there were weird stars, so with no seem to be star, with very luminous in radio, that they were called the quasi-stellar radio sources. So the quasar, so in radio, not invisible. And then finally, in 1963, Malcolm Smith measured the redshift of one of these bright nuclei, or in fact, it was just quasar, because the host wasn't detected at the time. And it realized that this object was a redshift of 0.16, so the luminosity of this object was enormous. And then it started the work on active galaxies. In fact, with respect to the unified model, this is a model that tries to explain the variety of objects that are put together in the family of active galactic nuclei. There are many, there are Siffert, quasars, BLACs, and so on and so forth. But the main idea is that where you have the central structure surrounding the supermassive black hole is this one. So you have the black hole in the center, then you have the accretion disk, then you have a kind of a donut, which is the dusty torus, which in here it's cutted and opened in the design for you to know, to be able to see what is in the inside, but normally it's covered. So in the inside, you have a region where there are clouds moving at very high velocities because they are very close to supermassive black hole. And then you have another region in the outskirts where there are another clouds, family of clouds that are moving at much less velocities. So in the inside, there's what we call the broadline region. and in the outside the narrow line region, because in fact, what the unified model says is that when you look at this structure through the dusty torus, you don't have access to the broad line region, so you just see the narrow lines in the optical. But when your line of sight is coming in this direction, you have access to the region of a broad line where the broad lines are originated, where the clouds are moving at very high velocity and enlarging the lines, and so you have a broad line galaxy, a ciphered one. This is a much modern view graph design or cartoon of what the unified model says, in which you can see that they are separated in top for radio galaxies, in which you see the radio jet, and on the bottom with no jet, and then you have the different objects, cipher2 or cipher1, depending on the line of sight, and then you have all the variety of radio galaxies. And in fact, the unified model is a simplified, as we try to make in astronomy, to simplified reality. It's a simplified version of what the reality in fact is, because the unified model cannot explain all the differences between objects. In fact, it cannot explain why jets are present or not. There is a relationship also with the orientation of the accretion disk and the degree of obscuration of the nucleus. And in fact, there are also a dependency with the mass of a central black hole on the rate of gas accretion onto the supermassive black hole. But in general terms, it's useful to understand what are the main differences between objects. One important thing to make you know is that starting this century, there was just at the end of last century, there was the finding that there is a relationship between the mass of a black hole and the mass of a central bulge, in the sense of having larger for larger of the two of them. And this was already said that it was needed, since the spatial scales are so different and are not connected. So it could mean that there is a connection between the formation and evolution of galaxies and the formation and evolution of supermassive black holes within them. And it started, as I was saying, in the beginning, in the end of last century. And in fact, there's a relation, excuse me for the tiny sizes there, but it's just, this is the mass of a black hole, and this is the velocity dispersion of the central galaxy, that in principle are not expected to be related, but you see there's a one-to-one relationship, either in this work by Ferris and Merritt or in Cormendi, in the review by Cormendi and Hall, which it's the same thing, it's supermassive black hole mass and luminosity, or in sigma. And then also I'd like to make you know also that in starting of this century, it was also the new view of AGNs not being a permanent stage of a galaxy, so just not having either active galaxies or normal galaxies, but the process of having an AGN is a normal process in the life of a galaxy, in the sense that you can have a normal galaxy and then you have processes that feed the supermassive black hole and make the activity start. And then you see this normal galaxy as a galaxy hosting an AGN, and then you see this very luminous source in the central region of the galaxy. So what about LINERs? LINERs stand for low-ionisation narrow emission regions. And these were classified as that. These are the nuclear regions of galaxies, and they were classified spectroscopically and proposed by Heckman in 1980. And this is characterized because the low-ionisation species have much higher luminosities with respect to the other ones than in other objects. Here you have a normal H2 galaxy here with the emission lines. Here you have the oxygen 3 H beta, H alpha sulfur nitrogen sulfur, sorry. And then you have a ciphered ones where you see that the oxygen 3 line is very important with respect to the oxygen 1, for instance, whereas in a LINER object, this is a prototypical LINER 1052. Then we learn much more about this object later on. We see that the oxygen 1 and the nitrogen lines and sulfur lines have much more intense. So these are LINERs. And from the beginning of the study of LINERs, it was already clear that they were normally or most generally hosted by early type galaxies with less luminosity than ciphered galaxies, and with a continuity in ionization state and electron temperature. The problem there is a problem already to detect these objects, to be able to know that there is an AGN, a LINER AGN in a galaxy, because they are much fainter than the other AGNs galaxies. So the star population contribution is much more important. So you have to deal with that and take that into account, as we'll see in a moment. And if you have not that much extinction and contamination by single-nuclear star formation, it's really difficult to detect them. And these are some other examples of optical spectra for you to have a quick overview of how they look like for the different AGN types. You have a BL-LAC object where the continuum, the stellar contribution is almost not seen. It's just the active nucleus what we are seeing. This is a cipher 1 with the broad lines here, and the permitted for broad lines here, a cipher 2 where these lines are narrow. This is a mean quasar with also broad lines, and this is a LINER, and this is a normal galaxy with the star population of the galaxy clearly here. So images of those. I will talk a little bit of these plots that are called BPT, but for non-experts, BPT come from the names of three men, Baldwin, Filipenko, and Talevich, who had the idea of using the line ratios, the emission line ratios, and in the optical of lines that were close to H beta in this case and H alpha in order to the ratios to be independent of extinction, because they are very close in wavelength here and here. So they plotted the line ratio between the oxygen 3 and H beta in the y-axis, and then the nitrogen over H alpha, or sulfur over H alpha, or oxygen 1 over H alpha here. And these plots are very useful to distinguish between the ionization or origin, the process of ionization that are taking place in different objects. And here you see in orange the H2 galaxies, so galaxies where star formation is producing the emission lines. Or you have Seyfert galaxies here in these regions in dark blue, and you have liners in red here. And when models are put over these plots, we can see that different processes can explain the line ratios in here for liners, so the red region, and they can be either the non-star photoionization by an AGN, or shocks here, or stellar photoionization by post-AGB stars. So the problem would be to be sure that we are talking about an AGN when we are dealing with a LINER nucleus. But in fact, if we detect broad lines, very broad lines in liners, it's a signature of having an AGN, or other things that I'll show you in a minute. So this is another much modern version of this. These are almost 300 galaxies, LINER galaxies from the Khalifa survey, and here you see the position of the liners is very clearly detected in these plots. And but I'd like to stress that I'm talking about nuclear liners, because since shocks or post-AGB stars can explain the Emission-line origin of these line ratios, there are also regions in galaxies out of the nucleus that have LINER-like optical spectra, but they are not. Of course, they are not LINER nuclei because they are out of the nucleus, and then they are produced by shocks mainly. So what we did was just to be able to work with a clean sample of AGN liners, were to analyze the X-ray data for a sample of 82 liners with this kind of information, either from Chandra or from XMM, and we made a classification of these objects in either an AGN candidate when a point-like source was detected in the hard X-rays, or a non-AGN candidate where we had no such a detection of a point-like source in the hard X-rays. So we ended up with having 60% of the sample with having this point-like source, so being an AGN liner, and the remaining, which were candidates, but we didn't know. We also used information at other wavelengths, since, for instance, having broad H-alpha lines, or having compact with some kind of properties in the radio emission, and then we concluded a 90% were AGN. So we are dealing always with liners belonging to this sample. So we are the sample of AGN candidates. So we are sure that we are not mixing with other phenomena in the nuclei of these galaxies. So then outflows. Why talking about outflows? The outflows can be also produced either by AGN or by star formation processes. But in the case of outflows produced from AGN, they are one of the fundamental processes by which the central supermassive black hole interacts with its host galaxy. And they have been suggested to be ubiquitous with the AGN population. For instance, you have some examples here, but they are always talking about high luminosity AGNs. LINERs were not included in those studies. And they are very important to explain the feedback from the AGN, either positive or negative. We're talking about positive feedback when the impact of the outflow produces more star formation, or negative when it stops and produces quenching. And this is very much related, thought to be very much related with the process of galaxy evolution and the transformation from the green valley to the red sequence for galaxies that I'm not talking about. But anyway, very important for understanding how galaxies evolve. And outflows have different flavors in the sense that they can have different sizes, different phases. So gas phases from neutral to molecular neutral gas or ionized gas, and also luminosities or powers. So here you have a sketch of how outflows work. Here you have the supermassive black hole and the accretion disk, and then there's the Rhodeland region, the torus, the cigonuclear disk, the narrow line region, and the extended narrow line region. And here you see, I don't know if you see the numbers from the. Do you see that at the end of the room? You see the numbers here, because these are the scales that goes from parsec scales in the torus to tenths of parsecs in the single disk, from 100 parsec to 1 kiloparsec in the narrow line region, and so on for the different phases. And these are the different phases: the atomic in blue, the warm ionized, which is the one I'm talking mostly about, and the hot ionized. So it's a complex phenomenon with different phases, as I'm telling you. But I will be talking about mainly the warm ionized gas. And here's a plot, quite a recent plot from Fiore et al. In 2017, in which here you see the mass rate in the outflow with respect to the luminosity of the AGN, the volumetric luminosity of the AGN. And there is a relationship. Here you have the ionized outflows, ionized winds in green, or molecular winds in blue. And so there's a relationship. It seems to be a relationship with these two quantities, the mass outflow rate and the AGN power, in the sense of having much more mass rate in higher power AGNs. But in this plot, they stop at 10 to the 43 ergs per second, which are normally high luminosity AGN. I will be talking about objects that are in this part of the plot, so they weren't, we didn't know how they were before. So are outflows as common as supposed to be in all the remaining AGN? That's a question that we wanted to answer. They are expected looking at that plot just before. If LINERs are residing in this size, in principle, we could expect to have the mass outflow rate being quite small, but we will see. And there were, as I was saying, no systematic studies of LINERs, except for these two from our own group, and mainly based on individual discoveries. Here I show you one of the examples of a LINER nucleus, a LINER galaxy, and a galaxy hosting a LINER nucleus. And here this is the HST image in narrowband H-alpha, and you see there's a bubble-like structure here that is, as you will see, connected to the presence of an outflow. So what I'm talking about is work that we've been done in our group, and I specifically put the picture of Laura Hermosa Muñoz here, because what I'm talking about is in a great part based on her PhD thesis. So the credits of the good is for her, for bad was mine, because I'm telling it. So if anything is wrong, it's my fault. So we made a threefold approach to study this problem of outflows in galaxies. First, based on imaging data, and parallel, we made the spectroscopic data with long slit, and we also made later on an integral field spectroscopy approach, which is much more useful, as you will see later. So first, starting with the imaging data that we had already started in this work in Masegosa et al. In 2011, we made an atlas of imaging that I'm going to explain here. In fact, what we made was an atlas of 70 nearby non-interacting liners, which was the largest atlas today of ionized gas morphologies. And here is one of the images that were obtained at the NOT telescope in La Palma with alphos. We combined images from the HST with images from not alphos. It's not that good spatial resolution, but similar for our purposes. And what we made was to consider that the outflow, the glimpse of an outflow could be traced by the presence of a given kind of morphology So we went for looking at these morphologies of the ionized gas distribution in galaxies. And here is the example of NGC1052, in which you see in contours the H alpha. It's the same as I showed before, but in contours with this bubble-like morphology, or in NGC1052, which is much more complicated. You will see why in a minute. And I skipped this because we had to make a special work for determining the background contribution, and this is also for the filter selection, but it's to get into too much detail. So what we did was just to categorize the morphology of this emission in 4 groups. Core halo for unresolved nuclear source surrounded by diffuse emission. Disk halo when we see phase-tone structures with H-alpha emission in spiral arms, or with rings or diffuse emission in the disks. Bubble-like morphologies that we identified tentatively with nuclear outflows seen as biconical or bubble-like structures or filamentary extensions, and also dusty morphology where we saw clear dust lanes obscuring the H-alpha structure in the inner regions. So difficult to see whether an outflow is there or not because of the extinction. And there's also the group of unclear where the morphology wasn't clear at all, but it's small numbers. So these are examples of these morphologies with the core halo, the disk, as you see here. The bubble-like example, this is NGC 5818, but 4438 also is this kind of morphology. And the dusty here with a very strong dust lane here. In the right, you have the sharp divided image of the continuum, and in the left, you have the H-alpha emission image. So what we found in percentage were almost 1/3 were core halo, almost 1/3 were bubble-like, and 20% of disk-like, and unclear dusty about 10%, and very small percentage of unclear. And this is one of the unclear examples, for example. In fact, the initial idea being that the outflows were here, we wanted to test whether it was the case or not. But for doing so we need to have spectroscopic information. We need kinematics, because otherwise these morphologies could be tracing anything else. Not anything, but many other things. So what we did was just to look at the literature for the kinematical information on all gas phases in the sample, in the 70 objects, and we found information for 86% of them. I'm not going into the details, but just almost half of the sample have a detection of an outflow or an inflow in any of the phases. So in fact, this means that outflows are present in 1 out of every 2 liners in half of the population. But in fact, the hypothesis of outflows only being connected with bubble-like morphology was not right, because in fact, when these are small numbers, so I'm dealing mainly with this part of the plot. Here you see how many of the different morphologies. This is the core halo, the bubble-like, the disky morphology have the detection of outflows from the kinematic information. And here you see that it is almost 50% of these two, irrespectively of being core halo or bubble-like. So outflows are much more are present not only in bubble-like morphologies, but also in core halos. And this is probably related to the age of the outflow itself. And so 55% of liners with any morphology but disky have a kinematical detected outflow, and for the disky the percentage is smaller, much probably because we are seeing a disk morphology, because we are seeing the structure face on. So the detection of an outflow is much more complicated than when you don't see face on, and you have the outflow much more extended and you can see it. So We also analyzed how the X-ray emission, the extended X-ray emission was related to the extended H-alpha emission in the objects. And we found that there was a kind of a tendency to trace the same thing, the same morphology. But in fact, in the same vein as before, the X-ray emission is not apparently correlated with the presence of the outflow, just in 23% of the objects. So the kinematic information is a need, obviously, for this study. So we had been doing in parallel a spectroscopic study with long-slit spectra of the sample galaxies, and in fact we analyzed just a subsample of 3/10 of objects, either LINER 1s or LINER 2, so that means having broad H-alpha or narrow H-alpha. And so we wanted to look for the signatures of the broadline region with comparing the space and ground-based spectroscopy, because we had, for some of them, both HSTs and CAHA spectra, visual spectra from optical spectra from CAHA. And also we wanted to look for a secondary, for the presence of an outflow from the kinematical point of view, as traced by the presence of a secondary component in emission lines within a given range of kinematical properties that I'm going to talk about later. So the kind of fitting we do is just we fit emission line with different components. And here you have the presence of a clear presence of a very broad H-alpha component here, which with a full width and maximum of about 10,000 kilometers per second here in H-alpha. And so the first component I'll explain later is, and the narrowest one is associated with the rotation of the galaxy, but then the secondary broader component is connected with the presence of the outflow, as you would see. So here is what I'm talking about. We made a plot because for the fit, we know the velocity with respect to the center of the galaxy and also the velocity dispersion as given by the full width and maximum of the line. And in this plot, we can see that this is a narrow component, so the primary component and the secondary component to the right. And what we see is that there's a relationship between the velocity. I mean, when we plot this with respect to this region is mainly occupied by galaxies in which for which the velocity and the velocity dispersion can be explained as come from the rotation of the galaxy because of the values that we are seeing here. But when the velocity dispersion is high enough, we can understand that as a presence of an outflow, so or an inflow when the velocities are positive. And here we have, in fact, what we found is that 1/3 of the objects that we analyzed with the long-slit spectroscopy were hosting outflows clearly in this kind of analysis. But we were dealing just with nuclear spectra. So in fact, to have a deeper view of how outflows work in these liners, we needed the whole mapping. So we need the integral field spectroscopy. So for attacking this problem, we made first a pilot study with one galaxy with a prototype of the the LINER galaxies, which is N1052. This is quite a normal, boring elliptical galaxy here in the image. I wouldn't say boring because if there's someone studying elliptical galaxies here, it would be. These are not boring. I mean that the image is not spectacular. I shouldn't say nothing. Okay, so. This is seems to be an elliptical galaxy, and here what we did was just to, I mean, there were previously integral field spectroscopy of this galaxy, but either with a field too small to understand, I mean, to see the whole picture, or with a slower spatial resolution, or with both spatial resolution but field not covering the whole galaxy, and we will see how complicated it is in this object. So here you have the Muse mosaic we got. We asked for having time with Muse, and we got it. And this is the overview of the map that we could see of the central region of the galaxy. And with this information, this is quite I mean, there's too many things in this plot, but just please follow me in where you have to look at. First, here, NGC1052, the data that we had enhanced was our own Muse DLT data with this spatial resolution, 0.2, spatial sampling, spatial resolution given by the PSF of 0.6, and this is the field of view. And then we also had obtained our own MEGARA data. Whoa, so we are almost done. Here. MEGARA data with a lower spatial sampling and it's not that good as with respect to that spatial resolution, and smaller field of view. In fact, what it is traced here in this box is the MEGARA field of view. And what we can have? We have this kind of spectral coverage. This is one of the new spectra of the central spaxel. Here, one of the outskirts spaxel here. So you see that we are going from about 500 to 5,000 to 9,000, and this is the coverage in spectral coverage of MEGARA data here. So what we need to do first, I was telling that before, is that we have a strong contribution from the stellar population here. So we have to subtract it before. So we have to make a model of the stellar the underlying stellar population that we fit just by masking out all the emission lines of all the problems we may have in the spectroscopy here, absorption, atmospheric absorption lines and so on. So here the masking is in gray, or I would say it's blue, but anyway. So we use PPXF to fit the stellar population, the underlying stellar population, which is traced in red in here. So in black, you have the original spectrum, and in red, it's the fit of stellar population there. So we will be dealing mainly then for analyzing the emission lines with the results of this subtraction. So with this information, with the fitting of the stellar population, we can derive the kinematics of these stars. So here we have the maps in velocities, and here is the insert of the MEGARA data. And the velocity dispersion of the stars as well. And here the same, the insert from MEGARA from the stars. So here, just from the kinematics of the stars, we see that there's rotation along this axis, which is the major axis of the galaxy. So in fact, it couldn't be that elliptical. We are more prone to think that it's quite a lenticular galaxy instead of an elliptical. And the rotation axis is this way. Okay. And then with the result of subtracting this stellar population, we can deal with the spectral fitting. And this is one example of what we do, of the kind of spectra we have. So they can be quite a bit complicated. And what we made it was a multi-Gaussian fits, and we made the corresponding maps of fluxes, kinematics, so velocities and sigma, and velocity dispersions, and excitation as well. And we had that for the ionized, so for all the emission lines, and also for the neutral gas traced by sodium D. And this is the kind of fitting we are doing. So here you say we have 3 components for H beta. We have the component in green and blue, and then a broader component in magenta. And this is the fitting for oxygen 3. For oxygen 1, we have so for all the emission lines. And this is what we found. This is the oxygen 3 map of the velocity dispersion, and this is the flux here. So we see here in black, you have the kinematical major axis of the stellar rotation that we've seen before. And this is the kind of structure we have. So you see that negative velocities in this side and positive velocities in the other one. So in an axis which goes almost perpendicularly to the major axis, to the kinematical major axis of the stars. And then we also have a structure here in velocity dispersion with much higher, this is an insert to see it better, much higher velocity dispersions, so widths for the lines that we will use that have also different line ratios. I'm not showing the maps, but this is the result. And this is for the first component, what we have here. We also have a secondary component that is aligned with the radio axis. There's a jet of about this scale here, and this component is aligned along the jet and there's another tertiary component, but it is not resolved, so I'm not dealing with it anymore. But I'll comment that at the end. And this is what happens for the neutral gas. This is the kind of spectra we have for the sodium lines, which have two components. I mean, it's a double line, so we fit the two. And for the fitting of this line, we don't have any indication of having a secondary component indicative of an outflow. So in fact, we don't know we are tracing the outflow with the nitrogen, with the sodium D line. Here is the velocity and the velocity dispersion, but what we see is also that it's aligned with the stellar kinematics. So no indication this signal to noise ratio of a secondary component. So this is a sketch or cartoon of what we think we have seen in this object. Here you see the major axis of rotation for the stars here. So with the red part and the blue part. And then we have this other region in which we have, for the emission lines, we have blue velocities and red velocities. And here we have the central structure, which had greater velocity dispersions that we call the butterfly, with an excess of imagination here, butterfly structure. And this is an enlargement part of this region in which we trace the radio axis, the axis of the radio emission here, and with the corresponding blue and red velocities. So the interpretation that we make is that we have a jet-driven outflow, which is produced in this very inner part, and this is directly connected with the radio emission, with the jet, and that we see in the secondary component for gas that has much higher densities than the other ones. I didn't show the plot, but it is in the paper. And we also have these other motions that could be boosted by this outflow, linear outflow, so giving rise to a bubble that goes in this direction. So we can also measure the outflow impact, the outflow properties, considering the luminosity of H alpha or H beta, particularly with H alpha. So from the luminosity in H alpha, we calculate that the gas entrained by the outflow is about, let's say, 2 times 10 to the 5th solar masses, with an outflow rate calculated with this formula, which is the formula normally used for calculating this with taking into account the velocity, the size of them, and the mass, which is about half a solar mass per year. We have a kinetic energy in the outflow of about 10 to the 53 ergs, and a power rate of about 9 times 10 to the 14th ergs. And if we compare these values with the power of the radio jet, which is given here, which is 2 times 10 to the 58, and with the volumetric luminosity of the AGN, which is 10 to the almost 43 ergs, we see that the scenario we are proposing is compatible with the radio jet being the originating this outflow, because the energetics is enough to be able to boost this outflow. On the contrary, if we calculate from the star formation rate, we calculate the kinetic power from supernova, which is 0.09 solar masses per year. This energy is not enough to power the outflow we're seeing. So it must be related to the jet. So in summary, the stellar velocity field is characterized by an older large-scale rotational motion, but we favoring an lenticular classification. The star formation and post-AGB scenarios from the line ratios that I have not shown is excluded, but it's mostly produced by the mixture of shock, excitation, and AGN activity. And the primary kinematic component is decoupled from the stars. The secondary component is in an outflow along the radio jets. And there's very tentative outflow in the neutral gas. And this is a clear example of how integral field spectroscopy is needed to try to understand what's happening in outflow in these objects. It's too much complicated just to be, to say just that I take the central, the nuclear spectrum, and I take everything from that. It's much more complicated than this. So we embarked in a study of a quite small sample of 9 objects, in which NGC1052 is also included with MEGARA, so an homogeneous study of these 9 liners with these local liners that all of them have luminosities, volumetric luminosities between 41 and 43 in log. So in the very bottom part of the plot, I showed from Fiore at the beginning, so that were not included there. You will see where they are at the end. And so covering the same kind of data I've said for 1052 with MEGARA. So again, the stellar population subtraction is absolutely needed to be able then to study the residuals in the emission lines, which are there. And again, we did it's a stellar continuum modeling with PPXF. Another example of line fitting. This can be quite complicated, and we use an objective measurement of how many components are needed because we can add as much as we would like and make a perfect zero residual, but it's not the aim. It's just the minimum number that is compatible with the noise of the spectrum. And in fact, we realized that we needed maximum three components for fitting the lines, plus in the very central region, in the region occupied by PSF, a very broad, so with full width maximum greater than 1,000 kilometers per second in some cases, as you will see later. So we have 9 objects, including 1052, and we have mainly 3 possibilities. I mean, the results are that we have 3 groups. Either a single Gaussian is enough, so we don't have any information. I mean, there is no indication of having an outflow because the singular Gaussian is tracing the rotational motion. Here you have the stellar kinematics, I mean, the velocities and velocity dispersions, so this is a flux. And on the bottom line, you see the kinematics of H alpha. So you see there's a kind of rotation along this same axis, and there's a kind of what we normally found in rotation objects with a peak in the velocity dispersion. And so we have 2 cases for which we don't need any secondary component, so no indication of having an outflow, which are these 2 galaxies, NGC1052 and NGC5055. And also, they don't have any indication of having a broad line region. Okay, but as I was telling at the beginning, they are AGN lines because they have hard X-ray, unresolved X-rays in the center. In this case, the kinematics is compatible with having a bar, and the other one is a nuclear disk. I won't show it. But another possibility is having the need of fitting 2 components for the emission lines, 2 Gaussians, and these are these 5 cases. And I'm showing here the case of 3245 here, which shows a clear rotation along this axis. And the sigma, the velocity dispersion shows some kind of structure that seemed to resemble that one in 1052, but at small scale. And a secondary component, very compact in this case, but all of them, by the way, almost all of them show the need of a very broad component, telling us that there is a broad region there. And this is the other case I want to show, which is 4278, not to mix with another. I know the name of galaxies are quite weird. I mean, just numbers. For me, there it's clear who is who, but not necessarily for the audience. So there's another galaxy, and they're starting from 4 and ending by 8 that I will talk about later, but it is not this one, right? In this case, we see the need. I mean, we need 2 components, and in fact, the secondary component is very much extended as it was in the other case. And in fact, the extension is along. This is the rotation, the axis of rotation here, and this is in gray. You see the axis where the radio jet is going along. So the secondary component again is aligned with the radio axis. And then there is the possibility of needing 3 components, which is the case of, this is the galaxy. I want you to think about this is a clear example. So I'm using this one later on quite a lot. So here you see the velocity dispersions of the stars. Then you have the primary component, the secondary component, and the tertiary component. And here you see this is the H alpha. This is the image I was showing from the HST, so with the bubble-like structure here. And you see that the secondary component and the tertiary component are aligned along the bubble. The secondary component is tracing mainly the outskirts of the bubble, and the tertiary, the central part. So when we use all the data from this sample to calculate the energetics, and this I put in this table in order that you learn it by heart. No, I'm joking, just it's not needed to look at all the numbers, just these ones here on the bottom, which are the mean values. So we see that in these 9 liners, this is the velocity of the outflow, this is the size, the mass, the mass rate, mass outflow rate, and the energetics here, the power here, and the rate, the ratio with respect to the AGN luminosity. So you see that the mean value, the outflows have mean values of around 300 kilometers per second in sizes of about half a kiloparsec, so they are not that small. They are entraining about 0.4 solar masses per year on mean values and with this kind of energetics, so compatible with being powered by the AGN, and with these with these densities that we calculate. And I say so because the following thing, this is the same kind of plot that I showed at the beginning by Fiore, where you see here the mass outflow rate with respect to the AGN volumetric luminosity here. And these are the crosses are the points from Fiore, but this is completed with more points for more galaxies from Byron and Netzer here as black triangles. So you see that in principle, very linear, for extragalactic astronomy, linear relation is not that linear when you consider some other objects. But in fact, there's also the problem that in this work, they use an electronic density, which is different from the ones used here. But anyway, but when we plot our points in this plot, the color points are our galaxies in here. So we see that the mass outflow rates are much larger than expected. Okay. This is 4438. This is the highest one. And it has a mass outflow rate which is very much comparable to galaxies that have AGNs that are 2 or 3 order of magnitudes larger. Okay, so outflows in liners, this is a very small sample, of course, but it indicates that outflows in liners could be much more impacting in the host galaxy because of the mass outflow rates that they are inducing that thought before. So since they are the most luminous population of AGN in the universe, they are worth exploring. And so even if this is a kind of a starting point, I think that we should consider that liners may have a role in the feedback processes connected with galaxy evolution. And so just to wrap up, the conclusion from these studies of 9 objects, we see the star kinematics are compatible with a rotation pattern, even if we had previously not only 1052, but other galaxies that were classed as ellipticals. So maybe there are more spirals than ellipticals. The ionized gas kinematics show complex behaviors with 7 over the 9 with more than one component needing, implicating the presence of outflows, with enhanced sigma regions with this butterfly shape that are co-spatial with outflowing components, with the outflow detections in 6 out of the 9, with the energetics of the outflows similar to higher power AGNs, and with tertiary component just in 2 galaxies that in both co-spatial with the radio jet. The line ratios, I didn't show the plots here, but both secondary and tertiary components are consistent with being originated by AGN or shocks, and with detecting the BLR component in 5 up to the 9. So we are dealing really with liner of 1.9 type. And this is the almost very last transparency. We are, in fact, since we have seen the usual connection between the outflow and the radio jet, we're making a specific study of the radio jets in a sample of about 40 galaxies, which is the theme of the thesis by Marta Puig-Subirà. And we are starting with this case, for which we have got data with Merlin, and also we are waiting for the data from VLA, and we are dealing with the energetics and the connection between the ionized gas and the radio continuum and the synchrotron emission, and this is work in progress. So I hope that Marta one day will show you what the results are. So thank you very much.
Questions?
Yes.
So it's a sort of legend question. In the last plot, I believe it was, with the updated data. Yeah. Why do your galaxies have 2 points?
2 points. Perfect. I was expecting someone ask the question, so thank you. This is because the points change their position if the mass outflow rate is calculated considering a density provided by the line ratios from sulfur. So we had in the table the actual values from those relations, or when we put the value that Fiore uses in his work, which is a fixed value of 200 centimeter minus 3. So this is just to have an idea how the points are differently placed when considering different. I mean, in here, the error bars are the true error bars are much larger than shown by any of people here, because there are a number of assumptions to calculate the energetics on the mass outflow here, because some of the things that you have to consider, for instance, is the orientation, the deprojection of your outflow. And it's absolutely difficult to make that. So the error bar that you would need to include there would be high. And there's also the question of the electron densities. So we just put as an example how this changes when considering different electron densities.
I want to ask, which is the mass regime of this liner? Because I see that your points are like displayed to the left, but there are low luminosity galaxies. So
low luminosity AGNs, not low luminosity galaxies.
AGNs. So it could be expected that for galaxy.
They are not smaller mass galaxies. They are galaxies with normal. I mean, the range of masses is quite similar. So I'm dealing with. I mean, what I'm saying when I'm saying low luminosity, I refer to the AGN itself, not to the galaxy, to the host galaxy. Right. So there is no possible scaling with the mass of the host. Was it your question?
Yes.
Okay.
Other questions? Yes.
Thanks for the talk. I have a question from the basic, like, as you explained that AGN is at the center. I am speculating if there is possibility of more than one AGNs at the center, and how the scenarios will be different in that case.
There are cases where you have the merging of two AGNs and you have two AGNs and you can detect them in spectroscopy because you have the two components of the lines. It could be quite difficult for this because we have excluded explicitly galaxies having merger morphology. So we think that the possibility is quite low. So we're dealing with a double AGN nucleus. It's point-like in X-ray. There is no 2 points.
Other questions?
Thank you very much for the talk. I was wondering, since you have this awesome data, is anybody looking for smaller structures, for example, ULX bubbles, if it's even detectable? Because
I don't think so. I don't think the spatial resolution is enough to look for ULX bubbles. They are not that close.
I see. And talking about ULXs, since ULXs also have been proposed for outflows and also as ionizing sources, when you're subtracting the star population, you subtract just normal stars, or subtract also X-ray binaries, stripped envelope binary stars that can be ionizing?
No, we are just using normal stars. I mean, the population of normal stars, it's determined by the fitting itself. The PPX fitting provides you with the star population that you are using. But in fact, we weren't interested in analyzing the star population itself. We just wanted to be able to subtract properly the underlying star population with because it can be degenerated. So we weren't interested in extracting any conclusion from the star population, just to have a good subtraction in order to have clean emission lines in the spectrum.
More questions?
Yes. So I find it quite interesting that the outflows you find, I think, are quite far from the canonical expectation we have. But the axis of the outflows, at least in the two examples you have shown after, is quite misaligned with the 90 degrees as you would expect. So it basically almost is along the rotation axis where the velocity gradient you see for the stars, suggesting that your outflow is propagating in your disk of the galaxy.
Not necessarily. I mean, there are cases where, for instance, 1052, the axis is almost, it's not perpendicular, it's not aligned either with the stellar rotation. So it's producing an outflow, a bubble, an outflow of wind, which is in the polar direction, so perpendicular to the major axis. But the main outflow itself, the jet of the radio jet, is not aligned with the major axis. So we have I mean, it's quite ill-determined, the projection effect that you can have. So we have started to, I mean, we also made the calculations taking into account that the axis could be much closer to perpendicular or much closer to the disk, and the numbers change quite a lot there. But it's the same for all the other points. So that's what I'm saying, that the error bar here are quite high.
So there is no relationship with like the ones you find which have very high outflow rates. They are not the ones that are misaligned.
No.
No questions. No? Yes.
It's actually something about your work, but the parent sample, it's very odd to me looking at this plot because it's a very limited range of luminosities. They have like some sort of, because it seems to not have any sort of luminosity evolution or dependence on the masses. What kind of sample, like what were they, what are those?
These are mainly Seaford galaxies, and in the other plot they are using also quasars and objects which are much higher luminosities. So that's it. And they are also using different constraints for the densities, for the electron densities as well, and different models. So we put that together just to have an idea of how different this can be.
Other questions.
But for molecular, in the plot that I showed at the beginning, where they were shown also the relationship of molecular outflows, so just at the very beginning of that one here. These are the ionized outflows, and also with X-rays here. So this is a line I'm using at the end from Fiore, but there is also a line here for molecular winds that are much more massive than the ionized gas winds. And there seems also to be a relationship there's a kind of relationship there. Either if it is the same for every AGN, it's not clear at all.
There are no questions, so yes.
I thank you for a nice talk. I wanted just to ask you about imaging and possibility of detecting outflows associated with the AGN just based on the images. So I assume that you need a high resolution, you use the AGST, but we are living in the era of James Webb, Euclid, and new infrared images. So do you think that with this you could somehow go deeper and to try to find candidates with AGN outflows based on the near-infrared images? There
are some cases that very much resemble, and there's a one-to-one relationship when we see clear bubbles like the one in 4438. It's okay, but it's also, we also have objects that don't have such a morphology and have outflows. So I think the images are wonderful, but they are not enough.
Last one. Yes.
Presence of bubbles, does it have to indicate a bubble? Or
a bubble-like morphology. I mean,
yes, a bubble-like morphology.
Bubble-like morphology doesn't mean that you have a bubble. So, I mean, morphology is morphology, and images can be misleading.
We have one more. Yes.
Thanks for the talk. The question is related to one slide that about the kinematic of the outflows in the different types, like or halo and these ones that you said that you find different kinematics in different wavelengths. I don't know, like kinematic outflow. I don't remember exactly. Yes, this one. I think the next one, maybe. Yes, that in some wavelength. So for different types, you find this. So they are close with the wavelength.
The meaning of this is that when we make the search in the literature, we considered not only ionized gas outflows, but also molecular outflows. So that's what I mean with the wavelength range, because you can have the optical, you can have the near infrared, and you have near infrared images, or near infrared spectroscopy, and you can have ALMA data, and you have the CO outflows and things like that. So that's why the meaning of the different wavelength. The case that we are doing with the MEGARA is just the ionized gas. But in here, when we looked for the presence of outflows as from any information that we could gather, it was comparing with the morphology.
And for some of the different morphological types, you find like outflows in one wavelength or the other. So
no, there is no. We don't have enough data to make it to make statistics on that. We just gathered everything, and sometimes there are cases where you have molecular outflows that are tiny outflows in the ionized gas, and the opposite. So, but we don't have numbers for making statistics.
Okay, so as you know, we have the party for Guadalupe. So downstairs, not pizza today, but something better apparently. And then at 2:30, Isabel will actually give the first of the year equity, diversity, inclusiveness talk. So we welcome them to come back. So before finishing, let me thank Isabel for the fantastic.
Thank you for the invitation.
Yeah.